One really important thing that we've already seen with reducing systems of linear equations in matrix form is these things that we're going to now refer to as the standard basis vectors. So anytime you see the ones along the diagonal and zeros everywhere else, there's actually a lot more to that than just that tells us that a system has, one or no or infinitely many solutions. These standard basis vectors actually in R2, remember this means 2 dimensions. All that means is 2 dimensions. The 1, 0 vector and the 0, 1 vector would just be vectors that point 1 unit in the x direction. That would be 1, 0. And the other one would be 0, 1. And the reason those are valuable is because they're 1 unit long and they are pointing in the direction of the 2 axes. So in essence, they represent the 2 perpendicular axes. R3 would be the same idea, except each vector just has a single 1 to point in one of the 3 directions and not in any of the other directions. So if we visualize this as 3 axes, and I'll just refer to these as x, y, and z, then the 1, 0, 0, remember these are in the order of x, y, and z, that would point 1 unit in the x direction. I'll just draw all these lines now. 1 unit in the x direction, no units, 0 units in the y direction, and 0 units in the z direction. 0, 1, 0 would point 1 unit in the y direction, 0 units in x, and 0 units in z. And then finally, as you can imagine now, 0, 0, 1 would only point in the z direction. And once again, they make up the 3 axes that we have. In general, in Rn, okay, in linear algebra, we often talk about kind of higher dimensional spaces. Rn just means that there's going to be n of these components. So n by 1, there will be n minus 1 zeros and only 1 1. So that gives you n total values. Okay, so now what we can do we can't really represent this or draw it because we can't see beyond 3 dimensions, but you can kind of see that the 1 is in every single position with zeros everywhere else across all of those vectors. Now the important and valuable part of this is that every vector in n dimensions can be written as a unique linear combination of the standard basis vectors e1 through en. As an example, in other words, what we're saying is that if you're in R2, then you have 2 basis vectors, e1, which, no surprise here, it's just where the index just represents where is your 1, and it's, in this case, in the first top component. E2 would just be same idea, except the 1 would be in the second component. And these 2 vectors, you can write any vector as a linear combination of this. For example, 5, 4, to get the x component to become 5, well, you'd have to scale the 1, 0 vector by 5. That would not change the y component because the y component is 0, and you can scale 0 by anything you want and not change it. And then plus 4 times 0, 1, right? So it's pretty trivial, actually, to write these vectors as a linear combination. As another example, let's say that we are in R3, and our vectors in R3 would be E1, again, would be 1, 0, 0. E2 would be, second component would be a 1. The others would be a 0. E3 would be the third component is a 1. The other components are 0. And for instance, if you wanted to represent, say, -3, 4, 8, you might imagine, you can control the x component by scaling 1, 0, 0. Control the y component by scaling by 0, 1, 0. And the z component by scaling 0, 0, 1. So this is valuable. Every single vector can, in n dimensions, can be represented by the n standard basis vectors in that dimension. So we looked at an example of R2 where we had E1 and E2. R3 would have E1, E2, E3. R4 would have E1 through E4, etc.